Hello, hello. Yeah, I'm still trying to get my setup done. Okay, so if you can hear me, just type in the chat. Okay. Okay, great. Yeah. Okay, so this is just our first hardware design lab. I haven't actually gone live on YouTube like this before, so I'm having some little technical issues. It won't be like this by next time. So by next time, everything will be set up properly. And yeah, so before we start, I intend to record this session also. And okay, okay. So we'll be brief into this class. We'll just do an introduction and we'll see how everything goes. Okay, yeah. So everyone is welcome in today's session, and this is actually PCB Mentor, and I'm Joseph Obona. A hardware design engineer, as you guys know. And also, we are starting our hardware design lab session. So, the hardware design lab session is actually a YouTube live space where I teach on hardware development, PCB designs, and some system integration setups. So, that's what I do here. And we'll just start and see how it goes. So, for today's session, we'll see how today's session goes. Then we just proceed from there. So in our hardware design lab today, we'll be looking at a multi-cell lithium battery charger system. So this session will actually have two parts, or maybe three. We're looking at a multi-cell lithium battery charger. And in this first part, we'll be talking about, we looking at how the systems will interact, how the IC we are going to use, and we'll also try to draw schematic and every other stuff. Yes. So just for confirmation again, can you hear me? Just type on the chat, please. As I say, this is my first YouTube live, so it's kind of giving me a little technical issues. Okay. Okay. Can you guys still hear me audibly? Okay, no problem. I'll just proceed. Okay. So yeah, this is what we'll be doing, and um, the next slide we'll be looking at our system requirement, and we'll be looking at our system requirement, and we'll be looking at the different ICs and the main IC we are going to use and some key specifications. So here I have every professional design starts with requirements. Every professional design starts with requirements. When designing any circuit at all, when designing any product at all, you need to have a system requirement for that product. You can't just move into design without having a system requirement. The system requirement actually gives you a blueprint on what to do. It gives you a blueprint on the design. It gives you a blueprint on the components to use. It gives you a blueprint on different aspects of things and various things to use. You get, so that's very important. Then we have here, we are we are designing a multi-cell lithium battery charger system. Yes. So what does multi-cell means? Multi-cell means that the charger system can accommodate, can charge different um, lithium battery up to two, three, four, like that, and goes based on the um, charging circuit we used. I guess. Because what I will also tell you guys, the IC we are using, the IC we are using is a multi-cell IC. Yes. But we are going to design it in the configuration that it will be charging just a single cell. So why I'm doing that, it's for so we can actually be fast, but you can still configure it in your own way as a multi-cell. You get, so it's just little configuration to that you will do. I'll also show you how to do that. You get the multi-cell um, system design. So I'll show you guys that also. Then we have their key specification. Yeah, yes, it's recorded. It's recorded. It's recorded. So this is just our first hardware design lab. Told you guys earlier on, little technical issues on my side, but from next time, everything will be fine and good. Everything will be fine and good. Yeah, so some key specifications. So when doing a system design or when designing a product, you need to actually know the things that you need. So for example, you need to know the things that you need for that design. So we also have some key specification in our own design. And few key specifications here are the input voltage. So the input supply, the system can be supplied with an input range of from 5 volts to 17 volts. Yeah. You see, we have 5 volt adapters, we have 9 volt adapters, we have 12 volt adapters, we have um, 15, is it 15 volt adapters also. You get, so this our input voltage range. Then the battery is multi-cell lithium pack. You get, so the charging IC we are using is BQ24171 from Texas Instruments. Alright. I can also show you guys, I'll show you guys the IC later on. Then charging architecture is DC-DC based system. It's not an AC-DC based system. You guys, you can also ask questions in the chat. You can also ask questions in the chat. Yes, so yes. And this YouTube, this thing, you guys, this is the first time I'm doing it. So let's just manage for today how it's going. But from next time, it's going to be awesome. And yes, from next one, it's going to be awesome. I just had little technical issues, as I said earlier on. Yeah. So, as we proceed, the architecture, charging architecture we're using is actually a DC-DC based system They will have the target efficient and stable battery charging system. That's what we're going to design. So this design we're doing will do the basic component selection. We'll also do the schematic diagram. We'll also do the PCB layout, and we'll have our full entire system on ground. So I have here why these steps matters a lot. Without clear requirements, wrong, okay, without a clear requirement, you can actually choose a wrong IC when designing your circuit. You can also have an incorrect power sizing when designing your circuit. Your PCB and your prototype stage can also fail when designing your circuit. So you need a clear system requirement that will guide you on what to do so that you design your product in an efficient and in a more reliable way. I get in it. Then the next one, we have component selection. To have component selection, so the key components we're using here is the BQ24171. This is the major component we're using here, BQ24171. And I also want you guys to share this in live stream, share it to others also, so everyone can be everyone can be tuned in. Okay, sorry. You can also put messages in the chat. In the chat. Okay, someone asked why choose a DC-DC. So this just for effective effectiveness. We can decide to use an AC DC converter, but it will need more circuitry. If you're doing an AC DC converter, you need more circuitry. You will need to start doing um, a rectifier circuit that will convert an AC system to DC system. So it's kind of more demanding. So DC system on this scenario, it's more easier. So component selection, the key component we're using is the BQ24171. I can show you guys this also, BQ24171. So, sorry, let me open my Chrome. So the BQ24171, this is the IC we're using, and it's from Texas Instruments. Yeah, so this is the IC we're using, it's from Texas Instruments, and it's actually a standalone 1 to 3 cell 4 amp synchronous buck battery charger. And on DC, when we're talking about DC to DC systems, we have different DC to DC systems. Yes, we have the linear system, linear regulator systems. We have the switching regulator systems. And in the switching regulator systems, we have what we call the buck converters. So what the buck converters does is it actually steps down voltage. It acts, it steps down voltage. Yeah, so let's say your DC voltage is at your DC voltage, your source voltage is 24 volts. A buck converter can step it down from 24 volts to either 5 volts to either 12 volts to either 9 volts, depending on your configuration. Then we also have a boost converter. A boost converter actually steps up the voltage, it boosts the voltage to the required voltage that the system needs. You get. Then we also have buck boost converters. We have buck boost converters. So yeah, that is it for just that explanation. Then this IC we are using, it's a 3 cell battery charger IC. It can contain 3 cells. So it's always good. I always tell my students that when you're designing a system, when you're using an IC, always come to the manufacturer's website to check what the IC can do to check various stuff. You get the components, what the IC can do, and the various features in the IC. So that is that. Then what we can do again, I can check the product parameters and yeah. So I'll come later on this input voltage and all this other stuff. Let's let me go back to the slide. Yeah, the slide. Okay, yeah. So we have selection criteria. We have selection criteria. There are some things you ought to know. There are some things you ought to know before selecting component, especially if you're selecting power components. You get, let's say your voltage regulator, a buck converter IC, a boost converter IC. There are some things you ought to know first, especially in also in component selection. There are some things you ought to know. So yeah, one, we have the input and output rating. Then we have the efficiency. The input and output rating is actually the input voltage of the system and also the your desired output voltage you want. So based on your system, you select your IC. If you're using a USB, for example, a USB majorly uses 5 volts. So you need to make sure that the IC can accommodate 5 volts of voltage, and let's say your system needs about 3.3 volts output. Yes, then you know that the IC you're using should be able to step down the 5 volts to 3.3 volts. So that's what we mean by input and output rating. Then we also have what we, efficiency. Efficiency matters in most cases, yes. Especially if we are comparing a linear regulator and also um, a switching regulator. In terms of efficiency, a switching regulator is more efficient in large current application. A switching regulator is more efficient in large current application. Okay, sorry for that. Then we have thermal performance. Thermal performance is there also. Then we have system compatibility. The IC you're using, is it able to meet the system requirements? That's what you need to find out. Then we have availability and cost. You need to make sure that the IC is available in the market. I need to make sure that you select component based on cost. Also, let it not be so expensive that you can't actually purchase it. So that is things that you need to look and put in place. Then we have your core idea. A good component is not just technically correct, it must be practical in real world production. Not just about technical correctness, but it must be practical in real world production. That means when it's being produced in the real world, you should be able to what? Use it without it giving you any issue in the long run. Then the last slide I have there before we go into our design, industry real industry reality. Real engineering isn't always perfect. Real engineering isn't always perfect. Yes, real engineering isn't always perfect. Engineering is about constraints. We need to do, there are so many things that, so many constraints and things that we need to put in place when designing a circuit. There's some compromise also in terms of availability, cost, size of the board, the kind of technology to use. Are you using a through-hole technology? Are you using um, um, micro VS, are using HDI technology, are using SMD and others. These are various things that we need to put in place. They also have their engineering is about practical working solution, not ideal designs alone. You're saying it's about practical working solution and not ideal designs alone. Then some applications that uh, based on this industry reality, component availability issues. Again, most times you want to design a board, a circuit, and you have like component availability issues. You can have some thermal problems after prototypes. You can also have layout noise and EMI issues, then cost versus performance trade-off also. So that is it for the slide. Then we'll go into our design majorly. So we're using Kika 10. We're using Kika 10. We're using Kika 10. So I've actually created a project for this. If there are any questions, you can ask. I've actually created a project for this. Then what we're going to do now is we are going to get into our component data sheet. We are going to see how things work. We are going to see how we can start our design. We're going to get the components and maybe we'll just draw this schematic. If we won't be able to finish the schematic now, during our part two section, which will be next week, we'll actually round up the schematic. But part two is going to be great a lot. Yes, I told you guys little technical issues I had as I was starting, so it's kind of just kind of trying to cope with it. Yeah, so what we need to do now is so this is the why we chose this IC, this particular IC, the BQ24171 is actually is a multi-cell battery charger IC. It can charge multi-cell battery, but just maximum of three. Something you can also do, especially Texas Instruments, they have lots of products, and you can actually, if your system, for example, needs about five cells, needs about 10 cells, you can still check it out here on the Texas Instruments website. You can come to the product, their product the icon here. Then we look for battery management ICs. It gets into battery management ICs. Then you can look for battery charger ICs. You can select battery charger ICs. Then what you can do, another thing, it's so you can come here and this place is like a comparison chart or graph. It's just like a comparison chart. That's here the seat catalog, automotive. So you can choose non-power parts, power parts, this, that, and all this. Even the battery technology, battery chemistry, lithium-based battery. You can see a one cell, 2 to 5 cells, 6 plus cells. So you can select the number of cells based on your application, and it will give you the recommended IC for that application. So I'll also show you guys how to just do it. Let me go with 2 to 5 cell battery. Okay, so I'm in this part. So what you can do also is so here is like their product catalog based on this stuff we have chosen, their product catalog, and you can see on this point they say number of series cells. Here is 2, 3, 4, 5. This particular IC can actually um, charge up to 5 batteries. This particular one here can actually charge up to 7 batteries. Like it's just massive, and you can just choose also based on the input voltage, minimum input voltage, maximum input voltage, um, some other parameters here, battery charge voltage minimum, and this. And then you can also check their availability and their cost also on the Texas Instruments website. We also have some many other manufacturers. We have people like Microchip, we have the ST Microelectronics, we have the NXP. They also do these kinds of products. So it's not just limited to one manufacturer alone. Yes. So I will go back to our main IC. So these are our main IC. So what I need to do is the data sheet. I need to come to the data sheet so I'll just understand. few stuff here. The software is KeyCard. The software is KeyCard. No, no, TP4056. I'm not sure it can do the same job. Even though it will be able to do, but it won't be as efficient as this. Okay, so this is very efficient. So now when the data sheet, I'll give you guys a secret. What I normally tell my students is, I normally tell my students something. I tell them that for you to be a good hardware design engineer, you must know how to read data sheet. Yes. Like for you to be very good in hardware design, you must know how to read data sheet. It's very important and vital. Like there's no two ways about this. You must know how to read data sheet. Reading data sheet gives you an edge. Data sheet and reference designs, then you need to know how to do research. Again. So I won't be going through everything here. I'll just be doing some major stuff. I'll just give you guys little insight on what to do when you're in a component data sheet. So the first thing to look at is the features of the component. I guess. So it's always at the top page. The features of the component is always at the top page. So on this part here, we have so this is switch mode lithium ion polymer battery charger with integrated MOSFET and power part selector. What the power part selector means is it can either take power from the source, either your either your adapter or your USB points to um, you're using for the charging. It can take power from there to the load, and it can also take power from the battery itself. So that's what we mean by power path selector. So once the battery is charging, the power will come. Once the battery is charging, the system power now will come from the charging circuitry. Then once the charging is cut off, the system power will come from the battery. That's what that means. Then we'll also have some other parameters here, like is a 1.6 megahertz synchronous switch mode charger. So this actually is switch mode power supply. Sorry, switch mode IC. So that is why we are having 1.6 megahertz. Then the efficiency is up to 94. Efficiency is up to 94. Then the input operating voltage, you have 4.5 volt to 17 volts. So this is the input operating voltage. You can actually power it via USB connectors. Then adjustable charge voltage up to 3 series cells. See, up to 3 series cells. Then you can read all these other stuff here. These are very important. If you most times anything you don't understand on the data sheet, it's always good to go and do research about it. Anything you don't understand on the data sheet, it's good to do research about it. Like this here, what you're seeing here, automatic power path selector between adapter and battery is what I just explained. Is what I just explained. So it can either take power, the system that's connected to this can either take power from the battery, or when it's charging, it can take power from the adapter. We can read there, then, yeah, so the next thing to do, once you're done reading the features of the IC and you've confirmed that um, this IC actually meets up your system requirement, then you can start doing other stuff. You can start your designs, check other stuff on the design and all that. Yeah, it's very important. So another thing I tell students to check is the electrical characteristics or the specifications, absolute maximum rating. So these are another parts. So recommended operating voltage, input voltage, this is the range 4.5 volts to 17 volts. Output voltage, this is the range maximum of 13 volts. Then output current, this is the range maximum of um, 4 amps also, and some other stuff. But to just commence our design, what we are going to do is to commence our design, we are going to go to the application and implementation. You get? So what the data sheet also reveals it what the data sheet also reveals is the data sheet gives us a guide on how to design our product. It gives us like a secretary to use to get our desired outcome. And most times, the secretary is giving us, it will give us the support, I call them support components, like the resistors, the inductors, and others. It will give us the secretary that we need to design our board. Again, most times you might also be confused. Oh, why did they use this value? Why did they use 1K here? Why did they use 100K here? All those information are also available in the secretary, sorry, in the data sheet. Yes. So one other thing you need to do when designing your product or when using a reference design on the data sheet from the manufacturer, regardless, if you need to understand why things are done the way they are done, you need to also understand the pin description of that IC. You need to understand the pin description of the IC. So during the boot camp we had about a month ago, yeah, about 3 weeks ago, I explained all this. You need to know how to read. You need to know the function of each pin and how to know that is just by coming to the pin configuration or description on still on the data sheet. And this is it. Each pin here has a pin name, pin number, and a pin name. And you can see the pin number and the pin name. And it's actually telling us, if you have a question, you can put it down. It's actually telling us the function of that pin and how we can configure that pin to get our desired outcome. You see it? So I won't waste much time. I'll go back to the application and configuration. So this is the typical application for our system. This is a typical application. We can use this application, and if you check here, it's telling us on this point 12 volts input. This circuitry now is for 12 volts input, 2 cell battery, 8.4 volts, 2 amp charge current, 0.2 amp pre-charge termination current, 3A DPM current, and 18 volts input. Yes, in it. So this is a typical application. Now we can either use this, or we have another application that we can use, or we can use this simple application. But this application here is this typical application schematic with a single cell removable battery. Okay, so this application here is for a single cell removable battery. Let's say you want to use a USB for the system. You want to use a USB for the system to charge a single cell. You can use this application. And I think I'll be designing with this application. You guys can still work with this. This for the multi-cell. You can still work with this. No much difference. It's just the MOSFET connection here that they added and other stuff. Yeah. So we'll work with this. We're going to work with this. Okay. I'm reading the comments. Abiot said TP1456 is only effective for one cell. Why can charge up to three cells? Yeah, that charge current also. Yes, yes, yes. That's true, Abiot. That's true, Abiot. Okay, I'm still thinking. We can decide to use this for, we can decide to design this application, this single cell application here, or we'll design this multi-cell application here. So for me to be fast, I think I'll go with the single cell application, but I also want you guys to design the multi-cell application. You design the multi-cell application. Then what we are going to do next, the first thing to do now is to open our KiCad software. Then you need to set up your KiCad interface. You need to set up your KiCad interface. Yes. page settings, this revision version 1. What to like, which title now will I give it? I'll give it battery charger IC. No, battery charger design. Yes, battery charger design. Then the size of the page info. Then, okay. So what I need to do now, I will need to bring the component symbol. Note, if the component symbol is not on your keycard, you need to import it or you design the component symbol yourself. If you don't know how to do the design, I guess you can reach out to me. I have a free mini course on that. Yes. BQ24. Yeah, this IC. Look at it. I imported it not too long ago into KiCad. So this is what we're using. This is the components we're using. Okay. So what we can do now is we need to follow the reference from the data sheet we have. We need to follow the reference from the data sheet. And I think I will, let me divide, okay, let me bring out my main components first. Let me bring out resistors and capacitors and others. Resistor small. Okay. Capacitor. Okay, then each other component again. Inductor. L. Okay, this inductor. Then let me bring out my power and power symbol. And then bring out ground symbol. Okay. So we have this now. I just want to divide my screen a little so I can actually see the reference. Then, okay, I have a shared screen now. Am I still audible, guys? Okay, so we need to start from somewhere. So I won't just be, I don't just like copying and pasting reference designs. I would also like to know why things are connected the way they are connected, and we also, um, okay, thank you, Abiot. I also like to know why things are connected the way they are connected, and also um, yeah, we'll also be going through the data sheet to just get things done. Okay, so for the first one, let's start with our input here. This is our 5 volts. So this is 5-volt adapter. We'll be using the USB Type-C connector. You get, we'll be using the USB Type-C for us, the USB Type-C female power connector for our own application. So what I'll do, I'll go back to my library, components library, then I'll type USB. Uh, is this the type C USB C plug? Okay, this is the power plug. Just the power plug I need. USB C connector. I guess this also need. So this when we'll be using the USB C. I guess it will be here. That's for the 5 volts. Then we have a diode on this point. But first of all, before I do any connection, ACP. I need to know what ACP means. This pin ACP and pin ACN. I need to know what they mean also. So for me to do that, I'll need to go to the pin configuration on the datasheet. I don't just like connecting things blindly when I'm doing circuit design. I'll need to know why, okay, why is this connected like this and what this pin is for. So ACP and ACN, I come here, go to pin configuration. Okay, I'm at pin configuration, ACP. So let's see what they are saying concerning ACP pin. Okay, they say there it's ACP, adapter current sense resistor, negative input. Yes. Adapter current sense resistor, negative input. A zero point 0.1 microfarad ceramic capacitor is placed from ACN to ACP to provide differential mode filtering. An optional zero point 0.1 microfarad capacitor is placed from ACN to AG, sorry, to analog ground, which is AGND, for common mode filtering. Okay, what I'll need to do now, I'll need to confirm this. They did this, they gave idea on this, but so I'll need to confirm this from the secretary. I still come back to this point, application, and this is not the one we're using. We are actually using this. So we did not actually get any form of those connections, no 0 0.1, 0 point, or on those points. Yeah, but if you see, it was, they actually, the data sheet now, that pin configuration now was majorly for this system configuration, this typical system application diagram of 12 volts input source. I seen it. That's why they told us to add this 0 0.1 microfarad. So the pin description was actually right. But we ain't following this application diagram. We are following the application diagram for the 5 volt input. We are not following the application diagram for the 12 volt input. So we just needed to know what that pin is. So it's for current sourcing. Yes, it's for current sourcing. We need to know what that pin is before we start any other stuff. Okay. That is that. Then we'll have PVC, PVCC. We also have CMSRC. You can also check this out also on the data sheet and what it means. So what I'll need to do now is I go back to my schematic. I'll go back to the schematic. Then um, so the power is actually on this USB. The power is actually coming from the V bus. What I can do, I can use a net name, place net label. I can use a net name for this, but okay. Okay, I can use a net name for this. I can name it VBus. VBus. Then okay, put it on this point. Then we have we actually have we have a diode here. So this diode should be for reverse current, to block reverse current coming to this point. That's why they added this diode. I'm pretty sure that's why they added this diode, to block reverse current. So what I can do, I can also get a diode. I can just get a generic diode. Later on, we can look for a diode IC number. So D small, D small. Okay. Okay. Yeah. Okay, we have done that. So this is VBus. So VBus now is connected to ACP pin, it's connected to CMS ROC pin, it's connected to ACM pin and PVCC pin. Okay, so I'll need to take this VBus and run those connections. So I can just do this like this. Then CMS, 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 CM. Okay, this point. Okay, then we have another one which is PVC, PVCC pin. But the PVCC pin has a 4.7 microfarad capacitor. But I don't actually know what that pin is used for. I just need to confirm. Let me know what the pin is used for. I'll need to go to the pin configuration and function PVCC. So let's get a clear understanding what the pin is used for. So they said here it's charger input voltage. Yes. They say connect at least 10 microfarad ceramic capacitor from PVCC to PGND and place it as close as possible. So they gave us the value of cap to connect. You get on this point, 10 microfarad capacitor from that pin. But I'll still need to let me confirm this from our application, this other main application. You're seeing it. So on this application here, this is what they use. They use the actual value, 10 um, microfarad. But for what we are designing, our application is for 5 volts. Yes, our application is for 5 volts. And on the 5-volt system, they used 4.7. So we can still go with this since it's being given to us by the manufacturer. We can still go with this and our system will work as intended. Okay. We might not finish the schematic today, so we might continue next week or on Sunday. Or I can just put this here. I can copy this. Okay, let me just make it in a clear way. Okay, then this is change the value to 4.7 UF. This is 4.7 UF. Then I copy this, the ground. Then I've established this point. So I've done this entire connection that is here for this entire pin. I've done the connections. Then we need to move further. Okay, for this point first, let me do this. The ground, just connect the ground to this point. You can also connect shield directly to ground. Again, sometimes you can also put a 5 point. You can also put a resistor. But let me just connect it now like this first. Then we don't have any differential signal on this our system. So we put this not connected. All these pins are not really needed on this. So it's the VBus majorly that's needed. Yeah, so what do we do next? Let's think of the next point to go. Um okay, still at this point, they said here, yeah, we have, say at this adapter point, we have 5 ohms resistor connected to VACC. Sorry, connected to AVCC. AVCC. Let's get what that pin is for. AVCC. Go back to pin configuration. AVCC. So they said here that this pin 4 IC power positive supply, place a 1 microfarad ceramic capacitor from um, AVCC to analog ground and place it close as possible to ground to the IC. Place 10 ohms resistor from the input side to AVCC pin to filter the noise. For 5 volts input, a 5 ohms resistor is recommended. You're seeing it for 5 volt input, a 5 ohms resistor is recommended. That is actually why they added. So if we come back to the application diagram, the one we're not using this, we're using the 5 volt ones. Come back to the application diagram for the 5 volt. This is page 28. So they actually use 5 ohms resistor. You see, so that's why they use 5 ohms resistor, and they connected this to AVCC with the 1 microfarad capacitor, which they said also on the pin description. So what I can do now is, at this point, I'll take a resistor, Control D to duplicate, then okay, duplicate. I put this 5 ohms. I'll just 5 arrow, just means ohms. Put this here. Then, if there are questions, you can ask on the chat. I'm seeing your chat. And then I'll need a capacitor also. So this for this pin, so I can bring it to this point. Then I can bring it to this point. Just to reduce the wire count, I can use a net label. I can make this AVCC. So put it at this point here. Then copy. Then put our AVCC at this point, which is this. Then I can just drag it. Yes, still the same thing. So we are designing our circuits little by little. We are just following the manufacturer's guideline. This is how you design circuits, by following the manufacturer's guideline. You don't need to do so much stressing yourself. But always something is the data sheet that gives you major insight of what to do. That is why before I do anything, I always go to the data sheet, the pin description, to know why things are connected the way they are connected. You get to know why um, the they used a particular value. It's always on the pin description and other parts of the data sheets. Okay, since still on our design, which other points? Now we've gotten this point. So this point here, what is this point? OVP set. OVP set. We don't know. I don't know what this is. So I need to find out. I need to find out. This I'm teaching us in a way that even when you're designing from scratch, you need to you know what to do. Yes. So I'm not just trying to do things, copy and paste things. I'm just doing things, trying to explain things so that we just go through everything. You might also see the mistakes I'll make here. You see how I'll resolve the mistakes. The book stamp I held, that's just the same thing we did, and it was very majestic. So OVP set. Yeah, so let's find out what this pin. This is pin 18. Let's confirm pin 18, pin 18. Yeah, OVP set. That's pin 18, which is right there. Let's see what it's telling us. They say here, valid input voltage set. Valid input voltage set. Use a voltage divider. Valid input voltage set. Okay. Use a voltage divider from input to input to OVP set, that is the pin, to ground to set the voltage to set the voltage Okay. The voltage above internal 1.6 V reference indicates input over voltage, and the voltage below internal 0.5 V reference indicates under voltage. In either condition, charge, charge terminates and input N MOSFET per AC FET and Arubi FET. These are pin turn off. LED driven by start pin keeps blinking, reporting fault. Okay, this pin actually can be used to report faults. But the main thing here they say is valid input voltage set point. Valid input voltage set point. Use a voltage divider from input to this to set this voltage. So I'm going to confirm this now in what they did. So what I can do now is, let's go back to our application. So this is the main typical application here. And for this, they used, remember the input source here is 12 volts, and they used 1000 K. 1000 K. This is about a million ohms, and they use 100 K here for this. Okay, what I will do now is let me go to a voltage divider calculator. It's actually voltage divider they did here. Voltage divider calculator online. Then sometimes when you're designing your circuit, you don't really understand what's happening in the circuit. You need to do research. You need to check so many things. Either you use voltage divider, either you use Google AI articles. Yeah. So the voltage source here is 12 volts. The resistance, let me put it in kilo. Okay. Arrow one is 1000 and arrow two is 100. Okay, the output voltage, R1 is 1000, R2 is 100. The output voltage is 1 volt. The output voltage on this point is 1 volt. Then for this other circuit, 4000, 400 and 100. Let me confirm. 400. So the output voltage here is 2.4 volts. Okay, 2.4 volts there, then there on. Why did they choose that? Okay, so one thing to do also one thing to do also when doing design, you need to, if you don't understand something, you need to check. I can just copy and paste the circuit, which it will still work, but I just need to confirm why they did all that, which it will give you better edge when doing your design. So what I'll need to do, let me look for that pin. If there's any other write-off on that pin, I'll just go to find OVP set, if I can see any other information on this. Okay, they said here the input voltage limit. Okay, the input over voltage limit is adjustable the through this pin. Okay, input over voltage limit is adjustable through this pin. Then let me see if I can get other informations. Mhm. Okay, input, here is input over voltage. This provides protection to prevent system damage due to high input voltage. In this IC, once the voltage on OVP set is above the 1.6 volt ACOV threshold below the 0.5 volts, this charge is disabled and input MOSFET is turned on. So we also have another information here. When this pin voltage is from, okay, This pin voltage is from 0.5 volt to 1.6 volts to qualify the adapter. So this is what they're saying. It's for voltage over voltage input source. You can still do more research on that. Maybe I'll still check that later on for better clarification. Okay, they still say there that this pin voltage indicates the adapter is not valid. They're saying it. And many other information we can still get. Many other information we can still get. I'll still look for a way to search for other stuff to give us. But let's just proceed. Let's work with our reference that we're doing. So on our reference, we have on our application, will soon be done in the next 15 minutes, so should be done. At least with this, we have 400k and 100k resistor here from this point to this point. So I can just take the resistors, put one here, bring one, then put the value 400k, then here 100k, then put this here. Okay, then bring this. I can decide to just adjust them to this point. Okay, then for over voltage, yeah. Okay, we've connected. Then I can also bring this close. I can also connect this close here. Let me do this well. Okay. Let me use a net label instead. I'll name it OVP set. Am I still audible, guys? Just text. So as I said, the next one will be far much better because this I had little technical issues as I was starting. So it's just worried me a little. Then we have our ground here. So we are done with that point. We are done with this pin. We are done with this pin. Which other pin? Here we have V reference, and we have AC set. AC set. So let's check out these two pins. What these two pins are for? Go back to the data sheet, pin configuration, V reference, and AC set. AC set, okay, they say there is input current set point. Use a voltage divider from V reference to AC set to ground to set the value. And they gave us a formula. I won't be going through all this, but this is the formula they have given to us. If you look at the data sheet well also, you also see uh, the you see the values that they used and every other stuff. Then V reference. Let's see what V reference is for. So V reference here, it's 3.3 volts reference voltage output. Place a 1 microfarad ceramic capacitor from V reference to analog ground pin close to the IC. This voltage could be used for programming ISET, current ISET, and AC set and TS pin. You guys, you're seeing what they're telling us. So this is V reference, and it's actually giving us an output of 3.3 volts reference voltage output. You get, so they also told us how to do it. To place a 1 microfarad capacitor. which we are going to do. Okay, go back to our application. Go back to our application. Then, so yeah, okay, one microfarad capacitor and this, which is correct. So I'll take a capacitor. Sorry, this capacitor here is going to be 1 UF. Made mistake. Then take a capacitor. V reference. Where is V reference? Okay, V reference is here. I can put it at this point. Then take a ground connection. Put at this point. Then what again? Again, I'm meant to do here. Then we'll have a resistor from AC set. Okay, resistors from AC set. Then now resistor from AC set. AC set. Okay. So let me just keep this as a placeholder zero. Let me keep it as a placeholder 0 ohms resistor. Okay. Let me shift this a little. Okay, AC sets here to here. Then we need I will need the net label V reference, V reference. Put a net label on this point. Okay, we'll put a net label on this point. Then we'll put it. I'm just following the reference designs, so nothing strange here. I'm just following the reference design. Nothing strange here. Now I've achieved that. So what again? Shit. Okay. We have achieved that. Then we have for I set. This actually to set the current. So there is one other thing that the datasheet can also give you. On this point, you, if you read this point, this part very well, after this, you see where you have design requirements, see where you have detailed design procedures. They will give you things in details, why they use those components, capacitors, the inductors, and what to do also to manipulate your circuit for your intended application. You get, they will give you all that input filter, they will give you the formulas to use and every other thing to do. Okay, so I'm not going into all that now. I'm just showing you guys the guide. That's what the data sheet. That's the advantage of using the data sheet. That's the advantage. So for the I set is to set the current. Yes, and here the current is you can set the current based on either 900. Here they did either 900 milliamps or 500 milliamps. Majorly for USB. There are some USB ports that can also output up to 2 amp of current in the USB chargers and all that. So you can use it to set the current and all that. So we won't be working with this circuitry here. This circuitry here is like a variable circuitry that can fine tune the resistance of that. So we won't be working with this. We will just be adding our 100K and our 12K resistor on the I set. That is why it's also good when doing design, you know what to do. So not everything that they added on the reference design that you follow and you copy. But this part now, I ain't following this part because this part is for selectable current limit. And I don't really need that. I just need something that is fixed on my board. So V reference 100K and 12.1K. So this is just same circuit here. I just copy it. So I set, okay, I can bring it to this point. So here is 100K. Then here is 12.1K. Okay, yeah, you won't find this file of you need to Emeka, you will need to import the component. You need to import the component. So how to import it? I'll just do it briefly for you. You need to import the component. How you import the component? You can go to Snap Magic, Snap Magic, snapeda.com. You go to this point, snapeda, then you type the component you want on the search bar. BQ um, BQ24771. BQ24771. You type the component. Once you type the component, you click on it. Then you see it here as Snap Magic. Look at it at this point. So once you've seen it here, then you can click on this point. Then you can now download it. So this here, you see it. Once you've downloaded it, then you will import it. So how to import a component is you go to preferences. Once it's downloaded, it will be like a zip folder on your to be like a zip folder here. I just downloaded it now. To be like a zip folder, you unzip it, you store it in a directory, then you come to preferences, then you come to manage symbol libraries, then you come to this point, then you look for where the file is, where you put the file. For me, this where I stored it. Where did I store it? Hardware design lab, project, Lithium, card. You see it, then you click on it. Once you click on it, it will open, then you press OK, then done. Then you go to the library and you see it. So that's how it works. So that's for you, Emeka. Okay, so we are rounding up. So I just need to do this now. Okay, this point is V reference. This for V reference. Then this is for I set. I set. Okay, so I put the I set on this point, and yeah, it's actually so I've established these connections here. So what do I need to do again? This other one, I'll do this one lastly. Let me finish this section. So what's remaining here is this, and I guess this is for um we can add this. I can decide to add this. I can still decide to leave it. This is for temperature. TS. Let me just confirm. What does TS means? TS, 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 TS. I said a temperature qualification voltage input. Connect a negative temperature coefficient thermistor. Program the hot and cold temperature window. I will not really need this on the design. I will just leave that. Though it's important, but I'll just leave that. So what I'll need to do now again, I'll need to put this for this is the status light. We need the light emitting diode with a 1.5K resistor for status lights. Start at which point? At this point. So I'll just take a diode, light emitting diode. So I come to my component library, LED, small LED. So this at this point, okay, this is how it's connected. I can put it red LED. Yes, for status. Okay, take this here. Okay, we'll just establish our connections. The reference voltage. We're almost done. We're almost done. I won't do the other part. I'll stop at this other part. Yes. So we are done with this section. Then we'll save. We are done with this section. So this other part now, it's just easy to do. It's not hard. I just think I just need to finish everything before we end. I just need to finish everything before we end. So what again? This inductor, SW pin. I've already told you guys what to do before you do anything. Always can check the pin configuration and all that. So I won't check the pin configuration for you guys now. I'll just try to fast track everything. So um, so we have our inductor here. We also have the capacitor on this point to BTS pin. Okay, I can do something here. Let me copy this. Okay, I have a capacitor here. BTS pin. Then we also have, so they said this is optional. The diode is optional. Do I really need to put the diode? I guess I will leave. Let me leave it for now since it's optional. Let me just put things that are necessary. This cap. Now have another cap here. We have another cap here, capacitor here. Then we'll have a resistor. A resistor that is a 20 milliohms resistor. That is a 20 milliohms resistor at this point. Okay, 20 milliohms resistor at that point. I'm just being fast, so we'll round up. So connect. I'm following this connection now. Connect. Then um, we'll have another connection at this point. Then we have. Let me use a net label. Let me name SW. Okay, at this point. So connect the SW at this point. Then, now from next one, I'm doing this now so that our next session will enter our PCB layout. So I just want to have this class for 2 sessions. That's why. Then what are we going to do again? Okay, okay, BTST, BTST. This, and you can also come and watch the recording later on also. So I still put it at this point. I'm just following the reference now. No much thing. Now we have our SRP, SRP pin, SRP pin from this point. So SRP, this, put it at this point. So you guys can be putting your question now. So we are rounding up. Be putting your question. If there are any question you have, just start sending in your questions so that I can answer. So won't waste much time anymore. Send in your questions. Send in your questions. send in your questions. You can send in your questions, still announcing. Okay. Yeah, yeah. So I'm done. I'm literally done. I'm literally done. So this was left. Put this here. So this is 10 microfarad resistor, 10 UF at this point, and duplicate it. Yes. So on this point, you have 10 UF. So it's connected to ground. Okay. Then feedback resistor. This feedback resistor. Then 100K, 100K. I need to do this. I think we'll have 100K here. So this is the last component, or the second to the last component for feedback resistor. Feedback. Okay. I'll still arrange the circuitry very well later. So this for the feedback. Then this other point here is the battery itself. So what I can do now is I need to put the battery. I'll just come here. I can make it a, okay, let me put battery, battery cell. Let me use a battery cell. So this is where I'm going to put the battery. Okay. Then the feedback is coming from here. So I'll take this and I'll put FB. FB, come here, FB. Okay, then the last one is our system. So I want to also use, last one is our system where we can connect it. So I want to still use the USB connector for this our system. That's how I'm going to do it. Yeah, so I'll also be using the USB connector for this. That's how I'm going to do it. The system will have two USB connectors. Okay, align. I want it to rotate horizontally. There's a place. Okay. Um, there's a place. Transform selection. Okay, rotate clockwise. Okay, yeah, this is what I want. I wanted. Okay, so this system is coming from this place. So I can put system here. If there are any mistakes, okay. Sorry, let me change this to 20 ohms. My keycard just crashed. Imagine. My keycard just crashed. Ah, God. Okay. So I'm going to end here. I've already done those major circuitry for us. I'm going to. The keycard just crashed and it was actually unsaved. But I'll get back the circuits and we'll continue next time. So if there are any questions, you can put the questions. If there are any questions, you can put the questions here. I'll be done with the circuit by next time. Then we'll enter our PCB layout. And just know that this is just the first time we're doing this hardware design lab. It's when I started the session, had little technical issues, so it was just kind of I was kind of trying to put things together. Yeah, but on Sunday we'll be doing our design review on the community. We'll be doing our design review. Some people have already started sending their boards, so I'll be reviewing the boards for. I'll be reviewing your boards, the board you designed during the bootcamp program. I've gotten about 2 boards that are being designed already, so I still need more. Send in your boards. If there are any questions to ask them, and yeah, I think today we had a very good time. So see you guys next week Saturday. Sorry, next week Thursday, same time. Okay, so we'll continue our design review session. We'll continue our design section. Then on Sundays, we'll do our design review sessions. If there are no questions, then I think we'll end here today. So goodbye, guys. See you guys next time. Bye.